Hello friends, Mr. Burrell here. We're in the last lesson in this last trigonometry unit that we're going over. We've been talking about the law of sines and the law of cosines, finding the area of oblique triangles. Now specifically with the law of sines and cosines, what we're going to do is we're going to talk about some real world applications, some real world type problems that you can solve and model using the law of sines, or model using a triangle and then solve using the law of sines and the law of cosines. Objectives by the end of this lesson, by the end of this video, this is what I hope you're able to do. I hope you're able to use the law of sines and the law of cosines to solve real world problems. Pretty straightforward. All the mathy stuff associated with the law of sines and cosines we've gone over already. Now is the critical thinking part. How can we use the law of cosines and the law of sines in a real world problem to solve for something that we don't know? So there are lots of real world scenarios that can be modeled with triangles. Triangles pop up everywhere in the real world, in the natural world, in the man-made world, all over the place. And those problems can be solved, those answers can be found using the law of sines and law of cosines. I was exploring YouTube videos about application of the law of sines and law of cosines, and I stumbled upon this video of a bunch of architects talking about the law of sines and law of cosines. Architecture is just a small subsection of all the possible fields that you could go into that would use the law of sines and the law of cosines. But I loved this quote from this guy I saw in the YouTube video. Here's the link to the YouTube video, just so I don't get in trouble for using this quote. But he said, "Trigonometry is absolutely head-bangingly essential, unbelievably essential. I have used it every day for the past 6 months." So it's not only in architecture that you use trigonometry. It's used everywhere, all over the place. Just one example of how useful it can be. But I think one of the examples that I'm going to go over here actually has a little bit to do with architecture, the architecture field. But know that this is used all over the place. It can be extremely helpful. So my goal is to go over at least one law of sines problem, a problem where you might use the law of sines, and a problem where you might use the law of cosines. But here are some of the kind of basic steps that you would want to follow for solving real-world trigonometry problems like this. First, you want to draw a picture of a triangle that would represent the situation in question. Whatever's happening, if it can be modeled using a triangle, we draw a triangle to represent that situation. 2, we want to label the sides and the angles of the triangle that you know, given the information in the problem. So depending on what the problem gives you, the situation that's presented, label the sides and angles of the triangle that you know. 3rd, we want to identify what we're trying to find. Is it a side we're trying to find? Is it an angle we're trying to find? What is it we're trying to find? And 4, you're going to need to determine if you need to use the law of sines or the law of cosines, or your knowledge of just plain Jane right triangle trigonometry, or a combination of all 3. Maybe you'll need to use the law of sines, the law of cosines, and right triangle trigonometry in order to solve. So we're going to kind of use all of our trigonometry knowledge right here associated with triangles, because the last step is solve and smile, because trigonometry is awesome. Okay, let's get started. There's not a real guided notes section associated with this, just the homework sheet. There's 8 problems on the homework sheet. I'm going to go over a couple of them. So the first one I want to go over is number 2 on that worksheet. So it says a laser beam with an angle of elevation of 42 degrees is reflected by a target and is received 1,200 yards from the point of origin. Assume that the trajectory of the beam forms approximately an isosceles triangle. Find the total distance the beam travels round to the nearest yard. What is the height of the target? And then this is the challenge part. What is the height of the target round to the nearest yard? Okay, so here's my laser down here. That's my laser. It says a laser beam with an angle of elevation of 42 degrees. So here's a laser beam, and this angle of elevation right here is 42 degrees. Elevation meaning I'm raising up from the ground. So I have an angle of elevation of 42 degrees, is reflected by a target, and is received 1,200 yards from the point of origin. So it's reflected off of like a target. So let's say here's like a little target. Here's a little target, and it's reflected off of that target to form approximately an isosceles triangle. So it's reflected off that target, and it's received 1,200 yards from the point of origin. So this distance right here is 1,200 yards from where it started. That's where the laser beam ended up. Assume that the trajectory of the beam forms approximately an isosceles triangle. Cool, okay. Find the total distance the beam travels. So the beam goes this far and then this far. So we're going to say this is A. Call this side A and this side A because they're both the same length. I want to find the distance to A because I want to find this distance plus this distance. That's what I'm trying to find, how far the laser beam travels. So we're going to start with that part. Okay, now let's fill in everything else on this triangle that I could possibly know. Well, this right here between the ground and this vertical line here, that's going to be a 90-degree angle, which means these two angles are complementary angles. They have to add up to 90 degrees. So if this is 42 degrees, this angle right here is going to be 48 degrees. Okay, cool. That's all fine and dandy. What else do we know? Oh, assume that the trajectory of the beam forms approximately an isosceles triangle. What do I know about an isosceles triangle? Well, I knew that these two sides were the same in an isosceles triangle, which means these two angles are the same. So this angle is 48 degrees. Whoops, 48 degrees. And I also know that all the angles on the inside of a triangle have to add up to 180 degrees, so this angle is going to be 180 minus 48 minus 48, which is 84. So this angle right here is 84 degrees. Okay, cool. So what are we trying to do? We need to try to find side A. I need to find what the value of A is because double that is going to be the total distance that the beam travels. The total distance that the beam travels, that's what we're trying to find. Okay. So what am I going to use here? This isn't a right triangle, so I can't use my basic right triangle trigonometry. I'm either going to be using the law of sines or the law of cosines. Well, do I at least know an angle and a side opposite that angle? Well, this is the only side I know. And I do know the angle right across from it. So I can use the law of sines. That's always my go-to. I want to use the law of sines if I can. So I'm going to use the law of sines, which states, remember that the law of sines says A divided by the sine of A is equal to B divided by the sine of B, which is equal to C divided by the sine of C. The ratio of each side divided by the sine of the opposite angle is going to be equal to the same ratio for all the corresponding sides. So, 1,200 divided by the sine of 84 is going to be equal to A over the sine of 48. Side divided by the sine of the opposite angle, side divided by the sine of the opposite angle. So I'm going to go ahead and solve this. If I cross multiply, I get, well, first let's type in what each of these values are. So the sine of 84, that gives me 1,200 divided by 0.9945. And then I have A over the sine of 48, which is 0.7431. Then I'm going to cross multiply, because I need to solve for A here. So 1,200 times 0.7431 is equal to A times 0.9945. Then I need to divide by 0.9945 in order to solve for A. So notice here, in order to solve for A, I took 1,200 times sine of 48 divided by the sine of 84. 1,200 times 0.7431 divided by 0.9945. Let's do that. 1,200 times 0.7431 divided by 0.9945. I can type that straight into my calculator here. Let's see here. And I get A is equal to 896.69 yards. Is that what I was asked to find? Not quite. I was asked to find the total distance the beam travels. So I need A plus A, both of those sides, or 2A. So 2 multiplied by 896.69, or 0.6, I think that was actually 6.5. I apologize about that. But close enough. I end up getting A equals 1,793.3. It says round to the nearest yard, so approximately 1,793 yards. 1,793 yards, 1,793 yards is how far that laser beam travels. And I found that using the law of sines. Cool! Okay, that's awesome. So this last part, this little extra bit, the challenge part, says what is the height of the target? Round to the nearest yard. So the height of the target, I'm wanting to find this side right here. Okay, well that's part of a completely different triangle. Let me draw this triangle over here. I'm going to erase my law of sines and cosines stuff. I want to find the height of the target, so I'm going to go ahead and draw this little mini triangle right here, just like this section right here, with the target up here, where I'm trying to find the height. This angle right here, the angle of elevation, was 42 degrees, and I just found that side A was 896, call it 896.7 yards. And I want, it says the challenge is to find the height. Well, the height from the ground just forms a right angle, so I'm not going to need to use the law of sines or the law of cosines. I can just use my right triangle trigonometry knowledge, my SOHCAHTOA knowledge. So this is the opposite and the hypotenuse side. So the sine of 42 degrees is equal to h over 896.7. Sine of 42 is 0.6691 equals h over 896.7. Then when I multiply by 896.7 on both sides, 0.6691 times 896.7, that gives me approximately 600, that comes out really nicely, about 600 yards. So the height of that target is 1,600 yards. 600 yards, sorry. Notice how this height was 600 yards. This distance, the height from where the laser started to where it ended, was 1,200 yards. It's half of that because this was an isosceles triangle. Whoa! Ah! So cool. So crazy. So we found the total distance that the laser beam traveled, and we also found the height of the target. All using the law of sines and our right triangle trigonometry knowledge. Okay, let's do another example. Number 6 says, this is number 6 on your homework, it says a roof truss is made in the shape of approximately an inverted V. The lengths of the two edges are 11 feet and 23 feet. The edges meet at the peak, making a 65-degree angle. Find the width of the truss. Okay, so here's my house right here. And the owner of this house has a really weird request, and he wants the angle of his roof to look approximately like this. The roof truss is kind of an inverted V, and these two edges are 11 feet and 23 feet. And the edges meet at the peak, making a 65-degree angle. Okay, so there's my triangle. I am trying to find the width of the truss. So this distance right here, side X. Call it X, call it whatever you want. Okay, well, how do I do that? That's all the information I'm given. How do I find the width of the truss? First question I'm going to ask is, do I know at least an angle and a side opposite that angle? No, this is the only angle I know, and I don't know a side opposite that angle, so I can't use the law of sines. I'm going to need to use the law of cosines. Remember that the law of cosines says a squared equals b squared plus c squared minus 2 times b times c times the cosine of a. So if I'm trying to find this side right here, x, I'm going to take the sum of the squares of the other two sides, so 11 squared plus 23 squared, minus 2 times each of those sides, times 11 times 23, times the cosine of the angle opposite the side we're trying to find, or the cosine of 65 degrees. Just like that. Oh, and this is x squared. I apologize. So all that stuff on the right side of the equal sign, I can just plug straight into my calculator. 11 squared plus 23 squared minus 2, parentheses 11, parentheses 23, times a cosine of 65. And I get 436.16. So x squared is equal to 436.16. Well, is that my distance? Is that the distance between these two? The width of this truss? That doesn't make any sense. Oh, yeah, because I have to square root both sides, because this is an x squared. So x equals the square root of 436.16, which is approximately 20.88 feet. About 21 feet is how wide that truss is going to be, how wide your house is going to be. 20.88 feet. Okay, cool. So that's the first part of this problem. We're done. We used the law of cosines. That was great. Challenge part says find the height of the peak. So I need to find this distance right here. Okay, it's all fine and dandy. Let's do this. So if I draw that little triangle over here, I'm going to go ahead and draw this side of the triangle. I know this side is 23. I just found that. I know this is a right angle. That's all I really know. So I could use right triangle trigonometry on this problem if I knew another one of these angles. Well, let's find, and again, I'm doing this one of many ways you could solve this. Let's find this angle, call it angle A, which corresponds with this angle on this triangle right here. Well, how could I find that angle? I could use the law of sines. Because 11 divided by the sine of A is equal to, we just found this other side, 20.88 divided by the sine of 65. We just used the law of cosines before. Notice now we're using the law of sines so we can find this missing angle. I can find this missing angle using the law of sines. 11 divided by the sine of A is equal to 20.88 divided by the sine of 65. So you can do this math in your calculator. I've done the math already, so I know that the sine of angle A is equal to 0.4775. You cross multiply, get the sine of A by itself, type in the sine of 65, get all that done, and I get the sine of A is equal to 0.4775. When I do the inverse sine of both sides here, in order to solve for A, the inverse sine of 0.4775 is 28.5 degrees. So this angle right here is 28.5 degrees, which means this angle right here is 28.5 degrees. Okay, well that's cool. Now I wanted the height of this, the peak of this truss. Now I can find that because if this is my angle here, this is the opposite and the hypotenuse sides, I can use sine to find that missing side. So the sine of 28.5 is equal to h over 23. The sine of 28.5 is 0.4772. I multiply by 23 on both sides. I get 23 times 0.4772 is equal to h, which is approximately 10.97 feet. Almost 11 feet is how high that truss is going to be. So notice in that problem we used the law of cosines, we used the law of sines, and we used our knowledge of right triangle trigonometry to find these different parts of this triangle that we were asked to find these different solutions. Ah! Pretty cool. Pretty cool. So that's all I've got for you in this lesson. There are 6 more problems on that homework assignment. Please don't hesitate to reach out to me if you have any questions, concerns, suggestions. But hopefully now you're able to better understand how to use the law of sines and cosines to model and solve real-world problems using triangles. There's a huge variety of problems that you can solve with these types of things. The examples in the homework are just a small subset of those examples. Feel free to explore this a little bit more. But I hope that that was helpful. I hope that you enjoyed it as much as I did.